Welcome back to the sixth part of this series of the concrete tank pool design. In the previous parts, we have defined all the load patterns and the joint patterns. Then we went ahead and assigned them, and we have also assigned all the uniform and non-uniform loading distribution. Now it's time to do the load cases. So we go up here and we say define load cases. Here we see all the individual loads. We don't have to worry about the modal analysis. This is only for earthquake, which we won't do in this case. We will leave it for another presentation. Okay, we then go up here, add new load case. We will call this load case 1 and full. Maybe it's a long name, just say case 1. Case 1 full. Now what are the load patterns for full? The first one is the self weight, so we add that, and then G super, which is the weight of the tiles and the surfaces, we add that, and then FWB, the uniform distribution of the water, we add that, and the triangular distribution FWW, we also add that. These are the load cases for case 1, the load patterns for case 1. Okay, then it is a linear static analysis, and we then say okay. Here you can see that case 1 full has been added to the list. We do it again, add new load case. Here we put it case 2. This time it's empty. What are the load patterns? The self weight is involved. G super is also involved. And then F soil plus the surcharge live load. And that is it. And then leave it as linear static analysis. By the way, these load cases type, there are heaps of them. As you can see, there's multi-step static, modal, response spectrum, moving loads, buckling, so many that we can speak about in the future. In this case, it's linear static analysis, and press OK. Then press OK again. Right, now it's time to run the analysis, run the model. How we go up here. Before we do that, it is best to save the file, so we can file, save as. I have already saved it under pool design, part 5 results, but you give it a name. I'm going to give it the same name, save over it. We go up here, that play button, and now what we do, we start up the top. We do not want to run any of these. We'll run one case individually. Each case will run individually. But let's get rid of all of them. So we go up to the top, press shift and down, and let's run, say, case 2 first, okay? Yeah, empty. So we come up to here, highlight these, and then run, do not run. So here we are asking the program not to run any of these except for the case where it's empty, and then press run now. Great, the program has completed the analysis. We want to say, look at the deformed shape. Click on the window that you want the results to show in. Let's say I want the 3D part, so click on here, and then go up here. We will see some results from the deflection. We click here for deflection and deformation. Click on the draw displacement contours. The results, here the resultant. So we can choose whether we want the results in the X or Y or Z, but this is sort of the resultant magnitude, is what we are interested in. And then show continuous contours, click on that. And we will also show the wire shadow. The wire shadow is a diagram of the initial position of the structure, or the tank in this case here. Okay, press OK. And here we see that the whole tank here has settled about 2.8 millimeters. In this case, it's 2.8 times 10 to the power negative 3 because our units is in kilonewton meters, our units here is in meters. Okay. If we want to see this on this sort of slab plan alone, so we come up here, make sure that we are on the XY. Okay, and then press deformation again up here and do the same thing. We don't need to say the Y in this case, but press OK. We'll go up here and draw displacement contours. So show contours and press OK. It seems that the whole tank has settled. Okay, now it's time to, let's say we want to check the moments. So we can go up here, again, shells and shell forces, F11, F22, all of these Fs are the shear forces, and the units is kilonewton per meter. And the moments, M11 is in the one direction, M22 is in the two direction, and the units is kilonewton meter per meter. I will go through it now. Say we want the moments in the M11, we click M11. And this is resultant forces, okay? Stresses is another category that we can look at. Press OK. And here you can see that the maximum moment in the system is 4 kilonewton meter per meter. Remember, it is per meter. Now, M11 means the moment around the one axis. Okay, what is the one axis? See the red arrow here, that's 1, 1. Okay, that's the moment around the red axis or the x-axis. So there's hardly any moments in the base of the pool here, minus 1.1 kilonewton meter per meter. It's intention. But most of the moments are in the edges here of the pool. That's around 3.1 and then 2.7 kilonewton meter per meter. This means that we need steel basically vertically. I will show you here what steel we need so we don't get confused. For the to resist the moments in the M11 direction, we need steel basically left to right of the page. Okay. M22 is the opposite way around, which we will see now. The steel for that is up and down the page. Moment M22 basically means all the moments around the green axis, which is the 2-2 axis. I will show you here. If we want to see the moments in the other direction, we go again up here and click shells and then M22. The maximum moment in that is around 5.6 kilonewton meter positive and intention 3.5 kilonewton meter per meter. Again, it's per meter, okay? And we can scroll around the slab and see what the moments are. We can also find the moments in the walls. So simply you can change the orientation to XZ and do the same thing. So XZ is the elevation of the wall and make sure that the local axis is on, so that when you do M11, you know that the moment is about the 11 axis. M22 is about the green axis. Okay, same idea. Come up here, shells, and check M11 and M22. And here in the walls, you have about, again, if you scroll around here, there's not much moments. If you go the other direction, the M22 direction, the maximum moment at the bottom is around 4.3, 4.9, almost 5 out here, 5 kilonewton meter per meter. Alright. We can also check the shear as well, the magnitude of the shear, and if it requires reinforcement. How do we do that? We say shells and F11 and F22, or you can say the F maximum. And in this case, you can also select the moment, the maximum moment as well in the system. If we say F maximum, and then just press OK, it's around 22.5 kilonewton per meter. Now, it is very important to tabulate all of these results. Okay, the way to do that is to go up here and say display, show tables. Come under here. I generally click the analysis results and then delete the ones I do not need. So with the joints, I need the displacement. Not really interested in the reactions at the joints. You can click that off, or the joint masses. Joint masses is good if we have earthquake loads. For element output, it is good to, let's have a look. We can, it's good to keep the element forces, which is kilonewton meter per meter or kilonewton per meter, and also the stresses. It's important to see how much stresses are developed in the shell element. Okay, element joint forces area, that's, you can click that off. And then over here, you don't need this. And the structure output, that's important because it gives you the total force from the structure on the ground, the total vertical forces and the moments under the ground. And that is important because we need to know the bearing pressure on the soil. Alright, then we say okay. Then we need to tabulate this in Excel, so we press OK. Then go up here, File, Export all tables to Excel. The Excel program will open automatically after that. And here we go. On the first tab, we have the base reaction, so you can see that the total force is 345 kilonewton. You divide that by the area, then you find the bearing pressure on the soil. We also have another tab for the element forces. Here we have all the forces, the shear force in the F11, F22 and F max. You can tabulate all that, go at the end of the table and find the maximum value of this table, and then design the steel reinforcements for this maximum value. In the element forces, we also have the M11 and M22 as well. So we come at the bottom of the table and find the maximum value as required. And then on another tab, we have the element stresses, which is very useful to find the maximum stresses at the top and the bottom of the shell. To see what, if we have the top as being negative, then the bottom will be positive, and so forth. Here is, by the way, you can see here the results is in kilonewton meter squared. With the stresses, you need to convert that to MPa. Okay, make sure you convert it before you tabulate it in your design results. You could imagine why I think kPa, because the units of the program was in kPa, or kilonewton meters. Okay, now let's see what the results are when the pool is full. So we can unlock this first up here and say okay. Go back to the play button. This time I do not want to run case 2. I'd like to run case 1 when it's full. Press that again. So it won't run anything except for the full, and then press run now. And we can see the deformation, the whole pool settled even further, about 6.3 millimeters in lieu of, the previous one, it was around 3 millimeters. So it seems that the pool, when it's full, is a much worst case scenario, especially for settlement. Again, we can go back into the results and check the moments like we did before when the pool was empty, or the M11 and the F11 and 2.2 and so forth. In this case, the moments, M11 is around, in tension 5.25 and 4.5 kilonewton meter per meter. If we look at the other side, M22, the maximum tension is 8 kilonewton meter per meter, which we need to design for the reinforcements. And most likely, probably minimum reinforcements will govern, especially in pool designs. So yeah, you need to check that with the relevant standards. Okay, I think this is it. That sort of concludes our series of this pool tank design using Sap2000. We hope that you enjoyed it and found it useful. If you have, please subscribe, like and share so that others may learn. And in the future, we will probably do some concrete analysis, concrete design analysis to display how to work out these reinforcements, and we need to check for torsion as well. That's something that we haven't done in this case here. Okay, thank you for watching and have a great afternoon.